S, 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 S. Like we assign all absolute configurations to all the chiral centers, and we have S, 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 S. Let's start doing a brain game. Now, give me examples of possible diastereomers I have for this compound. R, S, S, S. Thank you. One. I'll be asking one by one. Everybody will give me. You say R, S, S, S. R, R, S, S. Thank you. R, 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 S. R, 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 R. Is it correct? So have you got to see where your mistake is? So this automatically makes it an enantiomer because you change every absolute configuration. So I'm going to do this one. There are many of them. No idea. Okay, next. Who's that? S, R, R, S, correct? S, R, S, S. Many records. S, somebody has said S, R, S, S. S, S, R. So I'll stop here. I'll still ask all of you more questions. So these are called diastereomers. Now let us go to epimers. Epimers are special diastereomers. Epimers are special diastereomers. In the sense that for an epimer, only one chiral center is what changed. Now the situation can also be funny in the sense that you can have only one chiral center. Like, let me use this for and I'll use one as an example. Now, for this one, examples of epimers I can have is what? People that have not answered. Have you answered? Your own. Examples of epimers. Epimer of this compound. R, S, S, S. Correct? Another one. SSSR. SSSR. Correct? George. Epimer of this compound that has this particular configuration. RSSR. Is it correct? Why? Because this is a diastereomer. It's a normal diastereomer. We're looking at a special diastereomer in the sense that only one chiral center was changed. So I don't accept it. So you can try again. You know idea. So there are others. You can have SRSS. You can have SSR. Only one. Just if I want to do the three, just look for the one where only one was changed. Now for the enantiomer, this only has one enantiomer, which is what? R. Now if I have only one stereocenter with S, let's assume that S, the diastereomer will also be R because you changed everything, I did not. The enantiomer will also be R, even the epimer will also be R. So that is how we arrive at that. So what is the correct answer for that question? Let me write what the question said. The question said, what is the epimer of RS? So is it SSS? Is it correct? Is this one correct? Is this one correct? Is this one correct? Which one is correct among them? What is the question? I say, what is the epimer of this absolute configuration? The correct answer is B. Now, most people were choosing C. So So can you see where your mistake was coming from? So what is C? What is C? Enantiomer. C is what? Enantiomer, because you change S to R, change R to, and change S to. So the only one that is an enantiomer is what? SSRS. So go and take note of that. You must see it in this exam. Must. Which of these is false? A. All chiral molecules have stereocenter. Is it correct? Is it false? Okay, you said no. It's false. Not all chiral molecules have stereocenter. Some have chiral axis. Example is what? Actropysomas. So you know what the difference between stereocenter and axis of chirality? Can you remember? Stereocenter is a particular point where chirality occurs, but we can also have planar chirality and axial chirality. So these are places, we call them non-stereocenter places. So axial chirality and planar chirality does not show stereocenter. So a molecule can be chiral, but it doesn't even have any stereocenter. Example, actropysomas and chiral alleles. They don't have a specific carbon where you can hold it and say that this is a chiral carbon, but it is still chiral, correct? Now, B, chiral centers only occur in carbon, is it correct? No, it can also occur in nitrogen, sulfur, phosphorus, correct? Presence of one stereocenter does not render the whole molecule chiral, is it correct? I said presence of just one stereocenter does not make the whole molecule chiral. Is it correct? No, it's not correct. One stereocenter can render the whole molecule chiral. It just needs one point, either a point or an axis or a plane that is chiral to make the whole molecule become chiral. Now, enantiomers have the same A, magnitude of rotation, B, direction of rotation, C, physicochemical properties, D, A and C. Wrong. The correct answer is A and C. I know why I put magnitude of rotation. So let me explain why most I saw most of you were choosing C. Yes, C is correct, but it's not almost correct. Now let's start. The amino images, right? So these are enantiomer. Now, a rule says that if this one rotates flame polarized light to the right by 25 degrees, what value am I going to put here? Minus 25 degrees, because both of them are enantiomer. They must rotate at the same magnitude but different direction. So option A is actually correct. They have the same magnitude of rotation but then different direction. One will rotate to the right, one will rotate to the left. Now it says physicochemical properties. It is also correct. Every two enantiomers have the same, almost the same, not just say almost the same. Boiling point, melting point, solubility, they resemble each other. Now, which property makes them different? No, not even that. Biological activity. Because you have now discovered that one enantiomer may do something in your body, the other one may not do another thing in your body. When I was setting my OBJ, I actually said, let me introduce some parts in the theory, that even if you fail it here, go and learn your lesson. But you see that people didn't go to learn their lesson, actually. Now, I asked the question in theory. Why does enantiomer have different biological activity? Uzo will always tell you, why does this thing happen? Why? It happens, but what? Why? So we're going to look at why they have different biological activity. What compound was used as standard for relative configuration? No. Glyceraldehyde. G/N glyceraldehyde. I said, what compound was used as standard for relative configuration? The correct answer is glyceraldehyde, not lactic acid. So take note of that. Now, absolute configuration is what? I will not give you the option, but almost of you got it. R and S. Thank you. R and S. Now, which of these drugs have chiral sulfur? A. Aztreonam. B. Adalimumab. C. Ranitidine. D. Omeprazole. That one is very, very common, and you must see it in your exam. So let's go to the theory aspects. So I said, assign absolute configuration to this stereocenter marked as Aries. So let us assign it R and S. So there's something called Kahn-Ingold-Prelog rules. There are three scientists that came together. Kahn-Ingold-Prelog rules. Priority rules. Now, Kahn-Ingold priority rules say that if I have a stereocenter and I want to assign absolute configuration, I am only going to order the substituent in order of atomic number, not mass number. We are dealing with atomic number. Remember I said in the video that you must go back to your periodic table, because in your stage now, nobody will be giving you atomic numbers to actually know the one that is bigger or smaller. You must know that one should be bigger than the other. So we use atomic number. So this is a stereocenter. This is a stereocenter. Who can tell me the next thing I'm going to do? Yes, but there's one thing missing. I usually call it ghost. Hydrogen, thank you. So hydrogen is what? Ghosting. Yes, like as you ghost on WhatsApp, hydrogen is ghosting in this compound. Now remember that you dare not, right? I'm just choosing for theory purpose, because you must put that hydrogen. You dare not put an opposite bond, like you dare not put these bonds are opposite, but you dare not put them opposite themselves. They must be adjacent. So I'm going to draw one small line and put my hydrogen. Please take notes, because I saw one diagram now that somebody did that. You must have it at the back of your mind. You don't put these two hash and wedge bonds opposite each other. You put it adjacent each other. Now, let us start writing down the substituent. Remember I said that a chiral center, especially carbon, has 4 different substituents. If one substituent was repeated, it ceases from being a chiral center. So this is actually a chiral center. Why did I call it a chiral center? How I know my chiral center is that even though this is a ring, there's something called sidedness. This compound is sided because of this double bond. There's something to cause there, which I'm going to show you now. So the first one is what? Am I correct? I have hydrogen. Am I correct? Now I have carbon and 2 hydrogen. Carbon, 2 hydrogen. Carbon. How many hydrogens? Who said 2? 1. Thank you. Why is it 1? Because of what? Unsaturation. Unsaturation removes hydrogen. So because of this particular point of unsaturated, 1 hydrogen will be what? Removed. So here I will not have any hydrogen again, because the hydrogen that was supposed to be here was occupied by bromine. Then this is carbon and 2 hydrogen. So moving through this direction, I want to move through the first direction. So I have CH2, please name them for me. CH2, correct, correct. C, there's also a carbon here. So I say CBr, I put it in bracket, then CH2, excellent. If I go through this other direction, what should I be saying? Correct. CBr, yes. Correct. Yes. Correct. So let us now order them. So which one comes first? First position goes to what? BGS goes to who? What I said this gets what? A, is it not? Why does fluorine have A? It has the highest atomic number. Remember, we start considering the first one. So this one will get A. So now let me give you this trick. Don't mind hydrogen. Always give hydrogen last position. Give it carry over. Like once there's hydrogen, just place your G there, like nothing spoiled. So once you have your hydrogen, place a D here. Now the problem now is between these two people. So let us know who we go first. I'm going this way. C, is it not? I'll get bromine. Bromine is actually a very big atom. If I'm going here, C, before I reach bromine. So which one was shorter to reach my big atom? The second one, correct. So I'll give it my B and then give this one my C. So I will not actually clean this whole thing and see that this is A, this is B, this is C, and then this tiny hydrogen is what? D. But remember that you don't usually consider hydrogen. So just do for A, B, and C. Any direction is given, no problem. So I'm going to follow this direction when moving from A to B to C. So what direction? Clockwise or anti-clockwise? Anti-clockwise. So I assign this as what? S configuration. So I hope you understood this small thing I did. I took my time to explain it because you see this for you in your theory exam. So you know how you are going. And you must put a ring for you. Not even put chain. He likes ring. In fact, they put a drop for your absolute to identify whether it's R or S. Differentiate between absolute configuration and relative configuration. Now some of you are writing R and S and D and L. Yes, correct. But not sufficient. Insufficient information. Now the thing is that me as an individual, I may mark it for you. But him as an individual, will he mark it for you? That's the question you ask yourself. So it's an incomplete information. Now absolute configuration is assigned to each stereo center. R means rectus, S means sinister. So we assign them to each stereo center. But then native configuration is D and L, yes, but it is based on a particular compound called what? Called glyceraldehyde. These two configurations doesn't have anything to do with the optical activity. It's not because I have D-glucose. Okay, let's differentiate between two things now. That you know the kind of things that you might bring up. If I have let's assume R-glucose, D-glucose, assumptions, then tiny D-glucose. Which one do you think, like, which one should you be very, very sure that this is rotating it to the right? Which one should you be very, very sure of? Which one? Is it this one? Is it this one? Or is it this one? Okay, let's see. The last one. Stop by saying the second one. The correct answer is the last 1. If you check one of the videos, that's why I want to be highlighting all these small things for you. So that when you go back, look at them again, they are in the videos. Now, this tiny D glucose also means what? Plus. But tiny L means what? Minus. So if I have tiny d, small letter d, and small letter l, it is indicative of which optical activity is what? Occurring. But if I have big D and big L, like this one is textured, the other one is labeled. If I have big D and big L, it is not indicative of optical activity because the big D can actually be rotating to the left. It depends. It's not dependent. Even this arrow and S, they do not depend on plus and minus optical activity. But once I start seeing small letter D, small letter L, it means that the small letter D was rotating to the right and this one was rotating to the left. I hope I made sense. So this is called what type of configuration? Absolute. This is called what? Native, and this is what? Optical activity. So these two things do not indicate optical activity. So take note of that. Draw sawhorse projection for gauge butane. Now, in conformation, we have eclipse and what? Eclipse and what? Eclipse and what? Eh? Eh? No. We are talking about chapter 1. Talking about chapter 5 or I think chapter 6. I don't remember. But it's between 5 and 6. It starts with conformation. Now we have two types of conformation. We have eclipse conformation where the dihedral angle is 0 degrees and staggered conformation where the dihedral angle can be 60 degrees or 180 degrees. Now what type of drawing will I draw? I want you to give me this, then I'll give you back. Am I going to draw that one that looks like circle? Am I going to draw that one that looks like a horse? Ha! The question said, draw sawhorse projection. It didn't say draw Newman projection. Newman projection is the one that has that circle. While sawhorse has the one that looks like a horse. Now, the correct drawing for that is correct drawing for that. The correct drawing is so this is gauge butane. Why is it gauge butane? Now we have same butane. Same butane is eclipse conformation. When you look at the video, you are going to see it in details, like it was very detailed. Now why this is gauge butane? Remember I said that gauge is what 60 and 60 degrees, while anti is 180 degrees. Both of them are called staggered conformation. Why is this staggered? It's staggered because these two similar items are not in the same line. If they were on the same line, it is now called eclipse. You know what is eclipse now? What is eclipse first of all? What is eclipse? Eclipse means going on the same line and blocking each other. So this one was not blocking themselves, is it not? So the angle between this particular place and this line is approximately 60 degrees. So this is the diagram of the gauge thing. So when you look at the videos in depth, you'll be looking at all this line, understand more about them. So what type of stereoisomerism exists between these two things? Geometric isomerism. Now this is geometric isomers. Correct. Geometric isomerism. Now remember that geometric isomerism does not occur in terminal carbon with the same substance. So this one passes all the test. When you look at the video again, I know most of you didn't watch to that extent. So this is actually an eye opener to actually be very serious, but this is what it is. asking is test is exam question. This same thing. So examples of drugs that have this geometric isomerism include something like vitamin K, doxepin, ranitidine, and chlorpromazine. So these are some examples of drugs that possess geometric isomerism. There are still other ones. You can actually look at the videos and see many of these. So I actually drew 4 of these drugs and I showed how you can assign E and Z configuration. So they now say assign E and Z to this particular diagram. Most people, I will say most people are getting it actually. Assign E and Z. Now let us see how we can assign E and Z. Where is the double bond? This double bond is not. Now, at a particular double bond, you check the weight of the substituents. If substituents are very, very bulky, you give them A. So, if it's a bulky substituent, remember that there's an invisible hydrogen here, is it not? Always remember this ghost. Whenever you are drawing skeletal, you see this one? This is where invisible hydrogen, most of them are here. So always remember to highlight that invisible hydrogen. It will fetch you an I don't know if it's extra mark, but it will show you that you know what you're doing. First of all. So there's an invisible hydrogen here. So now this is a big substance, is it not? This is also another big substance. So I'm going to put A and A. Now remember that what is supposed to be here? Is it hydrogen or methyl? Methyl, correct. So methyl and hydrogen are lower substances, like they are not big now, is it not? So I give them B and B. So because A and A are on the same phase, and then B and B are on another side of double bond, I will not say that this is supposed to be C, but I will not use C. My next question will give me why I want to use C. Now I'm going to now assign this as what? Z. Z means what? Deuxamine. Z means deuxamine. So Z is what? Deuxamine. Now, when is it appropriate to assign E and Z instead of cis and trans? It's still in the video. Now, why it is appropriate to assign E and Z here is because this carbon and this carbon are involved in a double bond, is it not? Is it not? Is there any similar substance for both of them? That's the simple answer. So who can replace it in the way those of want? Who can the layman understand? These two carbons are involved in double bond, is it not? Their substituent and this one, are they similar? So replace it yourself. Why is it that there are sometimes it's better to assign E and Z instead of cis and trans nomenclature? So who can try? It's just a simple sentence. All these questions just quite simple answer. You don't even need any much difference. Try now. Correct. Just that simple sentence. The carbon involved in the double bond has different substances that are not similar. There's no substance that is similar in both carbons. So you just assign your E and Z. Remember that the one that are bulky, you assign them with what? A. The one that are less bulky, you assign them with what? B. You now start checking whether they are on the same side or different side. If they are on different side, what should I assign it? E, correct. Nth gen appropriation. Now, what is a chiral carbon? Just a simple sentence. It's a very simple question. I just put it there. What is a chiral carbon? 4 different substituents. Simple. That is a chiral carbon. Now, how many carbon stereocenters are present in this thing that looks like 3 or net? Yes, this is a compound. Yes. It's a compound. It's a compound. This is what you see. I lifted this thing as it is from Uzo's question, as it is. So how many stereocenter? We are going to name it, and I'll give you one small trick I have. So actually, if it's OBJ, I can cast it as fast as possible and give my answer immediately. Now, there is an invisible hydrogen. Am I correct? Is there any invisible hydrogen here? Yes. How many? One. Correct. How many is here? One. How many is here? Correct. How many is here? One. How many is here? Three. Correct. 3 invisible hydrogen. How many is here? 3. How many is there? 3. How many is there? 1. How many is there? 1. How many is there? 3. How many is there? 1. 1. How many is there? 2. How many is there? 3. How many is there? 2. How many is there? 3. Now let us start this qualification process. Now, all these candidates appeared for election, and PANSEC wants to disqualify them. Let us see how to disqualify all these centers. Now remember that whenever you have substituents that are similar or repeated itself twice, automatic disqualification. Is it disqualified? Yes. Correct. Is it disqualified? Yes. Who said yes? Why did you say yes? Was it disqualified? No. Because it's okay, this particular is disqualified. Yes, correct. They are very correct. Because this branch and this branch are actually similar. So it is what? Is this one disqualified? Correct. There is also H3 here. Is this one disqualified? This one. Is it disqualified? Is this one disqualified? This one is disqualified. Okay, this one is disqualified because it has 2 hydrogen. Yes. Is this one disqualified? This one? Yes. This one? This one? This one? Disqualified. Is it disqualified? Is it disqualified? Is it disqualified? Why is it? I was asking. Why is this one disqualified? Because he has 2 branches that look like 4. So automatic was disqualification. Is this one disqualified? Yes. Is this one disqualified? This one. This one. So the number of groups I have is 1, 2, 3, 4, 5. So 5 stereo centers. Remember this thing I want to give you now. That I will be very, very careful at the ending part. Because this ending part usually have similar substance that you may ignore. Because some of you might actually count this as the stereo center. Why in essence it has 2 things that shoot out. If I have something that still looks like this, 1, 2, and then I have 3, 4. Is this still a stereo center? It's not a stereo center. What if I have something that looks like this? Is this a stereo center? Yes, because these 2 things are not. So I hope you're understanding the idea because you see it in your exam. Now mention one drug that has phosphorus as stereo center and which disease condition is used to treat. Anti-cancer, cyclophosphamide. Cyclophosphamide, I think, is an alkylating agent. Then is it correct? Cyclophosphamide, antineoplastic, alkylating agent, yes, for cancer drugs. Remember when you reach 40, you see now about cyclophosphamide. But it has phosphorus as a chiral center. With the aid of diagram, I will not draw all the diagrams, but with the aid of diagrams, explain atrophysomas and name one drug that has atrophysomas. That exhibits this atrophysomerism. So let us look at one drug. So now, how does atrophysomas look? Who can explain how it just stops me? How does it look? What are what should present? It has phenyl. It can be naphthyl. It can be phenyl. It can be yes, area. Those things. Single, correct. Single bond attachment. Is it or perpendicular to each other? Is it or dies substituted at the auto position? Correct. Is it or different substances? Correct. Is it or they are bulky substances because what is called steric hindrance. Is it not? So all of you are correct. So it means that people read this atrophysomerism very, very because Uzo likes atrophysomas very, very well. So you see it in your exam. So this is how it looks like. You have a benzene ring with a single bond. Now be very, very careful in drawing this thing. Please don't go and draw this way for him and think that you passed. Oh, if you draw this thing for him, I don't know, he might be merciful, but be pretentious in the sense that make this one a little bit flat, like and then try and color this part very well. What is the essence of coloring it? Who knows? To show the perpendicularity. So it means that this thing was actually like turning, like it turned in a way, is it not? So I have substance X and the X, I have substance Y and Y. So they are actually this thing. This X and Y, it can be any substance, I don't know, you can put anyone you like. But they are actually bulky. Why are they bulky? They are bulky to cause what is called steric hindrance. What does steric hindrance do? Steric hindrance ensures that if this thing was turning freely, it will become conformation. And conformation is not what? Configuration. It becomes conformation. And you cannot separate any enantiomer. But because of this bulky substance, it will be very, very difficult to rotate. So because of that difficulty in rotation and increase in the energy of rotation, it is very, very easy to separate out enantiomers from atrophysomerism. So the chirality is coming from this double bond, which is affected by these disubstituted aryl groups at the auto position. Why don't you substitute at the meta position? Question. They are looking confused. Why don't we substitute at the meta position? Why is it must that it must substitute at the auto position? Why? Like I clean this thing now. Because people make that mistake and I want to correct it now. I have this, I have this. I have X, X, Y, Y. I still have my single, but people still draw this thing on the exam. Okay. Note that one thing I discovered the farm chem exam is that after chem exam, I destroyed Uzo. But at the end of the day, Uzo destroyed you, that kind of thing. So people make that this mistake in the exam because they will think that this is the auto position. So why don't you put it here? Because this will rotate freely, like this is a conformational compound, like there's free, like rotate anywhere you want. Okay, but if you have it at auto position, it contributes to the steric hindrance. So I hope you wrote all this thing for me, because that's what I'll be marking. All these small points. You must mention steric hindrance for me to give you that mark. Why this is causes enantiomer. Now what is spiral compound? Spiral compound is formed when the double bond in a chiral allene of what? Of atrophysomerism. Like where? Okay, and one drug that is active. Okay, an example of drug I have here. Look at it down. There are many of them. Telenzepam, lesinurad, vanco. I mentioned them in the video, so you can still go back to the video and look at them. So what are stereocompounds? Stereocompounds are formed when the two double bonds in a chiral allene have chiral allene. This is how chiral allene look like. So when you replace this double bond with ring, if I replace the double bonds in chiral allene with ring, spiral compound will be formed. Just a short sentence, and you score your full mark. Spiral compounds form when chiral allene, the double bonds in chiral allenes are replaced with what? Ring. It will form spiral compound. It's called spiral because it looks like what? Spiral. Like if you see compound that look like this, it's like one. Then you now start seeing something that looks like a wedge or ash bond. This is an example of how some spiral compound may look like. It looks like what? Spiral. It's not entirely fused and planar. It looks spiral because this particular bond went to the back. So it looks like something that was what? Spinning. That's why we call it a spiral compound. Examples of compound include fluospirillene, buspirone, spironolactone. I hope you have been hearing these drugs before. Spironolactone, irbesartan. These are spiral compounds. They contain these spiral moieties inside them. Now we are almost done. Differentiate between enantiomer and diastereomer. So what is enantiomer? What is diastereomer? What is enantiomer? What is diastereomer? People did. Okay, but still not. Correct. Enantiomer is okay. Enantiomer is non-superimposable mirror image, while diastereomer is non-superimposable non-mirror image. Let me write it down because just a simple sentence you need to give them. Like there are people that I saw that you change all the chiral centers for enantiomer and change not all chiral centers for diastereomer, still accepted. But if you want to shorten it in such a way that it will be matured, you say that enantiomers are both of them are non-superimposable mirror image, while diastereomer are non-superimposable what? Non-mirror image. Take note of these two keywords. Enantiomers are non-superimposable mirror image, while diastereomers are non-superimposable non-mirror image. You want to ask questions? Irbesartan. You didn't get the spelling. Irbesartan is an angiotensin 2 blocker. Okay, give figure G is esomeprazole. I think let me clean all this place because I've actually done justice to this company. So let me clean it. Spiral. No, I said all double bonds are replaced by ring. All the double, there's nothing like double bond for spiral. Double bond is all double bonds is the ring. So that's what makes spiral. And they can be hash more wedge bonds to show the spirality. Are you going to see that on that? So this is the esomeprazole. You can tell me what drug class esomeprazole belongs to? proton pump inhibitor for ulcer. Now, this is S-omeprazole. When you get to the last part of your video, you see how this one is the main acting omeprazole. Even if you give somebody omeprazole, all of them provide S-omeprazole. Look at them when we look at biological action. So now, the question was tricky, and I did it in also standard. What he was saying was, we draw this omeprazole for him. Don't touch this bond. Never. Don't touch it. Don't even put another bond. Because you put it judge and I saw it. Don't put any other bond. Don't touch any bond. But give me the inertium. Now, which other way should I be able to do it to get the inertium? Flipping by 180 degrees. That is the only thing he wants you to do. Very simple thing. Now, the other way was turning this wedge bond towards hash bond. But he said don't touch the wedge bond. That is a way instruction. If some of us were touching the wedge bond and changing it to hash bond, you got it because it's the inertium, but you failed it because you failed to adhere to the instruction. So let me show you how to draw this and draw it very, very well. So I would like to start from this. You can also start from these places. It's still okay. But what I used to do is I'll come to one side, put mirror. So that thing you see on the mirror when looking at yourself, analyze it here. Now, I'll start drawing. This one, should this come like this?